Tonight's peaceful exploration brings us face to face with something truly extraordinary. A brand new world discovered right here in our own solar system. A celestial wanderer that's been hiding in the darkness for billions of years, just waiting for the right moment to reveal itself to humanity. And what a revelation it is. Before we embark on this cosmic journey together, I'd love to know where in the universe you're joining me from tonight. Are you gazing up at the same stars that have watched over this newly discovered world for eons? Fitting, isn't it, that we're here together in the darkness, learning about something that's spent its entire existence in the cold, distant reaches of space? If you find comfort in these gentle voyages through the cosmos, or if tonight's discovery fills you with that quiet sense of wonder, I'd be ever so grateful if you gave this video a like and perhaps subscribed it. Helps this little corner of cosmic calm reach other stargazers who might need a peaceful pause in their day. Now, I do hope tonight's celestial tale isn't so fascinating that it keeps you from drifting off to sleep. But if it does, well, at least you'll have learned something remarkable about our solar system's newest resident before you slip into dreams of distant worlds. So settle in, take a deep breath, and let's begin. Because somewhere out there in the frigid darkness, beyond the realm of familiar planets, lies a story that's been waiting 4.5 billion years to be told. Meet Ammonite, our solar system's newest confirmed member, and quite possibly one of the most intriguing discoveries in decades. This isn't just another space rock tumbling through the void. This is something special, something that challenges what we thought we knew about the outer reaches of our cosmic neighborhood and whispers secrets about the very birth of our solar system itself. Now, you might wonder why we're calling it Ammonite. After all, that's not exactly the sort of name you'd expect for a distant world floating in the icy depths of space. But there's something beautifully poetic about this choice. Ammonites were ancient marine creatures, spiral-shelled fossils that tell us stories about oceans that existed hundreds of millions of years ago. They're windows into the deep, past-preserved fragments of life from when our world was utterly different. And that's exactly what this newly discovered world represents, a fossil not of ancient life, but of the early solar system itself. Officially designated as 2023 KQ-14 by the international astronomical community, Ammonite was discovered by an international team of researchers using the powerful Subaru telescope, perched high on Mauna Kea in Hawaii. This isn't just any ordinary telescope, mind you. It's one of the most sophisticated instruments humanity has ever pointed at. The star's equipped with something called the Hyper-Suprime. A camera so sensitive it can detect objects so faint and distant that they're barely whispers of light against the cosmic darkness. The discovery itself is part of an ambitious project with the wonderfully evocative name FOSSIL, which stands for Formation of the Outer Solar System, an icy legacy. And if that doesn't sound like something straight out of a science fiction novel, I don't know what does, but this is real science. Real discovery, and the implications are absolutely staggering. So what exactly is Ammonite? Well, imagine, if you will, a world that's roughly 136 to 236 miles wide, nestled somewhere between the size of a large asteroid and a small moon. It's not massive by planetary standards, but size isn't what makes this discovery so remarkable. It's where Ammonite lives and how it moves through space that has astronomers absolutely captivated. Ammonite belongs to an incredibly rare class of objects called sednoids, named after Sedna, the first of these mysterious worlds to be discovered back in 2003. To put this in perspective, there are only 4 known sednoids in our entire solar system. 4 that's fewer than the number of gas giants we have orbiting our sun. These objects are so rare, so elusive, that finding one is like discovering a new species of whale in the deepest ocean trenches. What makes sednoids so special is their orbits. These aren't the nice, neat, circular paths that we're used to seeing from planets like Earth or Mars. Instead, sednoids follow incredibly stretched out elliptical orbits that take them on journeys lasting thousands of years. Ammonite's closest approach to the Sun is about 66 times the distance between Earth and our star that's already well beyond the orbit of Pluto, which averages about 40 times Earth's distance from the Sun. But here's where it gets truly mind-bending. At its farthest point, Ammonite ventures out to 252 times Earth's distance from the Sun. To put this in perspective, imagine if Earth's orbit was the size of a coin. Then Ammonite's orbit at its closest would be about the length of a small room, and at its farthest, it would stretch the length of several football fields. It's an orbit so vast, so elongated, that it defies easy comprehension, and it's remained stable for billions of years, a testament to the delicate gravitational dance that governs our solar system. The discovery of Ammonite wasn't a moment of sudden revelation, but rather the culmination of years of patient observation and careful analysis. The first hints of this distant world appeared in images taken in March, May and August of 2023. Using the Subaru telescope, but confirming its existence required follow-up observations in July 2024. Using the Canada-France-Hawaii telescope, scientists needed to track this faint point of light across multiple observations to calculate its orbit and confirm that yes, this was indeed a new member of our solar system family. What makes this discovery even more remarkable is that researchers were able to trace Ammonite's presence in archival images, going back nearly 2 decades. They found it lurking in data from 2021 and 2014, captured by the Dark Energy camera on the Blanco telescope, and even in images from 2005 taken at Kitt Peak. National Observatory, Ammonite had been there all along, a patient sentinel in the darkness, waiting for humanity to develop the tools and techniques necessary to spot its faint signature against the star-filled sky. This extended observational timeline spanning 19 years has allowed scientists to calculate Ammonite's orbit with remarkable precision, and what they found is absolutely fascinating. Computer simulations indicate that Ammonite has maintained its current orbit for at least 4.5 billion years, essentially, since the formation of our solar system itself. This isn't an object that's been recently disturbed or knocked into an unusual path. This is a pristine remnant from the dawn of our cosmic neighborhood. The implications of this discovery ripple through multiple areas of astronomical research, but perhaps none more significantly than the ongoing debate about a hypothetical 9th planet lurking in the outer solar system. For years, astronomers have been puzzled by the orbital patterns of extremely distant objects like the other known sednoids. Their orbits seemed to be aligned in a way that suggested the gravitational influence of a massive, unseen planet. Something perhaps 4 times the size of Earth orbiting far beyond the realm of Neptune. This hypothetical world dubbed Planet 9 has been one of the most hotly debated topics in planetary science. Some researchers argue that the clustering of these distant orbits can only be explained by the presence of this unseen giant, while others suggest that observational bias or other factors might account for the apparent patterns. The discovery of Ammonite adds a fascinating new piece to this cosmic puzzle. What's particularly intriguing about Ammonite is that its orbit doesn't align with those of the other 3 known sednoids. While Sedna 2012, VP113 and 2015, TG387 all follow somewhat similar orbital orientations. Ammonite marches to the beat of its own cosmic drummer. This discrepancy is causing astronomers to reconsider their theories about what might be influencing these distant worlds. Dr. Yukun Huang from the National Astronomical Observatory of Japan put it beautifully when he noted that Ammonite's orbital orientation lowers the likelihood of the Planet 9 hypothesis if there truly is a massive planet shepherding these objects into similar orbits. Why would Ammonite be the odd one out? Why would it follow such a different path through space? But here's where the story becomes even more intriguing. Computer simulations suggest that about 4.2 billion years ago, roughly 300 million years after our solar system formed Ammonite, and the other sednoids may have shared remarkably similar orbits. Something happened during that ancient epoch. Some significant event that scattered these objects into their current disparate paths. What could have caused such a dramatic reshuffling of these distant worlds? One possibility is the passage of a nearby star during our Sun's youth, when it was still embedded in the star cluster where it formed gravitational interactions with passing stars, could have lifted these objects into their current elongated orbits. Alternatively, the culprit might have been a planet-sized body that once existed in the outer solar system, but was later ejected, taking some objects with it and scattering others into new paths. The discovery of Ammonite also highlights the remarkable technological achievements that make such finds possible. The Subaru telescope's wide-field imaging capabilities, combined with the Hyper-Suprime cam, represent the cutting edge of astronomical instrumentation. These tools can scan vast patches of sky, looking for the faint, slow-moving points of light that betray the presence of distant worlds. Finding objects like Ammonite requires extraordinary patience and precision. These worlds are so distant and so faint that they appear as mere whispers against the cosmic background. They move so slowly across the sky that it takes multiple observations over months or years to confirm their existence and calculate their orbits. It's detective work of the highest order, requiring both technological sophistication and human ingenuity. The international collaboration behind this discovery spans multiple countries and institutions, from Taiwan's academia, Sinica, to Japan's National Astronomical Observatory, from Canadian research facilities to Korean space science institutes. It's a testament to how modern astronomy operates as a global endeavour, with researchers sharing data techniques and insights across national boundaries, as we contemplate Ammonite's lonely journey through the outer darkness. It's worth reflecting on what this discovery means for our understanding of cosmic evolution. This isn't just another dot on an astronomical catalogue. It's a time capsule from the early solar system, a witness to events that occurred when our sun was young and the planets were still taking shape. The story of Ammonite reminds us that our solar system is far from fully explored, that there are still mysteries waiting to be uncovered in the cold, distant reaches beyond familiar worlds. Each new discovery like this one adds another piece to the grand puzzle of how our cosmic neighbourhood came to be, and perhaps more importantly, how it continues to evolve. The discovery of Ammonite also raises fascinating questions about what other secrets might be hiding in the vast emptiness beyond Neptune's realm. If there are only 4 known sednoids in our entire solar system, how many more might be out there, waiting to be discovered, drifting silently through the cosmic darkness like ancient mariners on an endless voyage? The rarity of these objects cannot be overstated. We're talking about a population so sparse, so elusive, that finding one is like stumbling upon a single grain of sand on an endless beach. The fact that we've now identified 4 of these distant wanderers suggests that there might be many more lurking just beyond the reach of our current telescopes and detection methods. What makes sednoids particularly intriguing is their apparent immunity to the gravitational influence of the known planets, unlike the objects in the Kuiper belt which dance to Neptune's gravitational tune, or the asteroids that feel Jupiter's mighty pull. These distant worlds exist in a kind of cosmic no-man's land, where the familiar rules of planetary influence fade into insignificance. This isolation makes them perfect time capsules, preserving the orbital characteristics they've maintained since the solar system's youth, while other objects have been jostled and perturbed by planetary encounters over billions of years. Sednoids like Ammonite have remained largely undisturbed witnesses to the ancient past. The numerical simulations that confirm Ammonite's orbital stability are themselves marvels of modern computational astronomy. Researchers can now run virtual experiments that span billions of years, watching how gravitational forces would have shaped these distant orbits over cosmic time. These simulations don't just tell us where Ammonite is now, they reveal where it's been and where it's going, painting a picture of orbital evolution that stretches across geological ages. Through these computational time machines, scientists have discovered that Ammonite's current path through space is remarkably stable. It's not spiralling inward toward the sun, nor is it gradually escaping the solar system's gravitational embrace. Instead, it follows a predictable elliptical dance that has persisted since the era when the first rocks were forming into planets. But perhaps the most tantalizing aspect of Ammonite's story lies in those computer models that suggest all 4 sednoids once shared similar orbital orientations about 4.2 billion years ago. This hints at what astronomers call a clustering event, some dramatic reshuffling of the outer solar system that scattered these objects into their current diverse paths. Imagine, if you will, the early solar system as a cosmic construction site, gas and dust swirling around our young sun, gradually coalescing into the planets we know today. But this wasn't a gentle, orderly process. It was chaotic, violent, and transformative. Massive objects migrated inward and outward. Gravitational resonances shifted entire populations of small bodies, and occasionally something truly dramatic would occur. The clustering event that may have separated Ammonite from its sednoid siblings could have been the passage of a rogue star wandering too close to our solar system. Such stellar encounters were far more common in the early universe, when stars were packed more tightly together in their birth clusters. The gravitational tug of a passing star could have been enough to lift these objects from their original orbits and set them on the elongated paths they follow today. Alternatively, this ancient reshuffling might have been caused by a planet that no longer exists. Some researchers speculate that our solar system once harboured additional planets that were later ejected into interstellar space. The gravitational chaos of such an ejection event could easily have scattered nearby objects into wildly different orbits. The very name fossil, chosen for the survey project that discovered Ammonite, reflects this deep connection to the past, just as paleontologists study ancient fossils to understand life's history. Astronomers study these distant objects to understand our solar system's evolution. Each sednoid is like a fossilized bone fragment from the solar system's skeleton, telling us about the forces and events that shaped our cosmic neighborhood. The technical achievement of finding Ammonite cannot be understated. These objects are so faint that they require the most sensitive cameras and largest telescopes humanity has ever built. The hypersuprime cam used in this discovery represents years of engineering innovation designed specifically to detect the faintest whispers of light from the most distant objects. Even with such advanced technology, the process of discovery requires extraordinary patience. Observers must take multiple images of the same patch of sky over weeks or months, looking for points of light that move ever so slightly against the background stars. The motion is so subtle that it's like trying to detect the crawl of a snail from several miles away. Once a candidate object is identified, the real work begins confirming its existence. Requires follow-up observations with different telescopes calculating its orbit. Demands careful analysis of its position over time, and determining its physical characteristics requires sophisticated models that account for how sunlight reflects off its surface. The international collaboration that made this discovery possible represents astronomy at its finest. Researchers from Taiwan, Japan, Canada, Korea, China, and other nations working together, sharing data and expertise across cultural and linguistic boundaries. It's a reminder that the quest to understand our cosmic neighborhood transcends national borders and political divisions. The naming of this object as Ammonite, after those spiral-shelled marine fossils, is particularly apt. Both represent preserved remnants of ancient worlds. Ammonites tell us about prehistoric oceans, while the celestial Ammonite tells us about the primordial solar system. Both are windows into time so distant that they challenge our ability to comprehend the vast scales of cosmic history, as we contemplate Ammonite's solitary journey through the outer darkness. It's worth considering what this discovery means for our understanding of planetary formation. The presence of these objects in the outer solar system suggests that the early phases of planet building extended much farther from the Sun than we previously imagined. The fact that Ammonite has maintained its orbit for billions of years also tells us something profound about the stability of our solar system. Despite the apparent chaos of planetary formation, despite the gravitational tugs and pulls of multiple massive worlds, despite the occasional passage of comets and asteroids, the outer reaches of our cosmic neighborhood have remained remarkably stable. This stability has allowed Ammonite to preserve its ancient orbital characteristics, like a message in a bottle thrown into the cosmic ocean billions of years ago, by studying its current path through space. We can read that message and learn about the conditions that existed when our solar system was young. The discovery also highlights how much we still don't know about our own cosmic backyard, despite centuries of astronomical observation, despite space missions to every planet, despite increasingly sophisticated telescopes, we're still finding new worlds in our solar system. Each discovery, like Ammonite, reminds us that the universe is full of surprises waiting to be uncovered, the implications for the planet. 9 hypotheses add another layer of intrigue to this discovery. For years, astronomers have debated whether a massive, unseen planet lurks in the outer solar system, shepherding the orbits of distant objects like a cosmic puppeteer pulling invisible strings. Ammonite's orbital orientation, which differs markedly from the other known sednoids, complicates this picture. If Planet 9 exists, and if it's responsible for clustering these distant objects, why would Ammonite be the exception? Why would it follow such a different path through space? This doesn't necessarily disprove the planet. 9 hypothesis, but it does suggest that the story of the outer solar system is more complex than we initially thought. Perhaps there are multiple mechanisms at work shaping these distant orbits. Perhaps the gravitational influence of a distant planet is just one piece of a much larger puzzle. Some researchers now suggest that the clustering of sednoid orbits might be explained by other mechanisms. The collective gravitational influence of many smaller objects in the outer solar system could potentially create the observed patterns without requiring a single massive planet. Alternatively, the apparent clustering might be an artifact of observational bias. We tend to discover objects in certain parts of the sky more easily than others. The debate over Planet 9 illustrates how scientific understanding evolves. Each new discovery, like Ammonite, forces us to reconsider our theories and assumptions. What seemed like compelling evidence for a hidden planet yesterday might look different in light of today's observations. As technology continues to advance and our ability to detect faint, distant objects improves, we can expect more discoveries like Ammonite. The outer solar system is vast and largely unexplored territory. There could be dozens or even hundreds of sednoids waiting to be discovered, each one a potential time capsule from the early solar system. The Subaru telescope and other cutting-edge instruments represent just the beginning of a new era in solar system exploration. Future surveys will scan even larger areas of sky with even greater sensitivity, potentially revealing a hidden population of distant worlds that have been invisible to us until now. These future discoveries will help us piece together the complete story of our solar system's formation and evolution. Each new sednoid will add another data point to our understanding of the forces that shape the outer regions of our cosmic neighborhood. The story of Ammonite also reminds us of the importance of archival astronomy. The fact that researchers could trace this object's presence in images going back nearly 2 decades shows the value of preserving observational data. Astronomical archives are like libraries of the sky containing hidden treasures waiting to be discovered by future generations of researchers. As we drift toward the end of our gentle exploration of Ammonite's discovery, it's worth reflecting on what this tells us about our place in the universe. Here we are inhabitants of a small rocky world orbiting an ordinary star in an unremarkable galaxy, and yet we've developed the ability to detect and study objects so distant and faint that they're barely whispers against the cosmic darkness. The discovery of Ammonite is a testament to human curiosity and ingenuity, our species' relentless drive to explore and understand the universe around us. It's also a reminder that the cosmos is full of wonders, waiting to be discovered, that our solar system still holds secrets that have yet to be revealed. Somewhere out there in the cold darkness beyond Neptune's realm, Ammonite continues its ancient journey, a silent witness to the birth and evolution of our cosmic neighborhood. It carries within its orbit the memory of events that occurred when the Earth was young, when the first complex molecules were forming in primordial oceans, when the stage was being set for the eventual emergence of life and consciousness. In the quiet moments between heartbeats, between the gentle rhythm of breath and the soft whisper of wind through leaves, Ammonite drifts through space at speeds that would make our fastest spacecraft seem like leisurely strolls through a garden. Yet from our earthbound perspective, this distant world appears almost motionless, a patient wanderer taking centuries to complete what we might consider a single lap around our cosmic neighborhood. The sheer scale of Ammonite's journey challenges our ability to comprehend the vastness of space. If we could somehow shrink our solar system down to the size of a large city, with the sun at the center and the familiar planets scattered around like landmarks we might recognize, Ammonite would be found wandering in the distant countryside, following a path so elongated that it would stretch from the city center to far beyond the horizon and back again. This is the realm of deep space, where sunlight arrives as barely more than starlight, where temperatures hover just above absolute zero, where the familiar warmth and energy that drives life on Earth becomes nothing more than a distant memory. Yet Ammonite has called this frigid wilderness home for longer than complex life has existed on our planet. It has witnessed the formation of mountain ranges and their erosion into dust, the rise and fall of entire species, the slow dance of continental drift that has reshaped our world countless times over. The discovery process itself reads like a detective story unfolding across decades. Those initial observations in 2023 were just the beginning of a careful investigation that would eventually span nearly 2 decades of archived data. Astronomers had to become cosmic archaeologists, sifting through years of stored images, looking for the faint signature of this distant world hiding in plain sight among the stars. Picture the meticulous work involved in this celestial detective story. Each observation represents hours of telescope time, careful calibration of sensitive instruments, and painstaking analysis of data. The researchers had to distinguish Ammonite's faint glow from the countless background stars, track its subtle motion across the sky, and separate it from the noise and artifacts that inevitably creep into astronomical observations. The fact that Ammonite appeared in images from 2005, 2014, and 2021, before its official discovery in 2023, tells us something profound about the nature of scientific discovery. Sometimes the answers we seek are already there, waiting patiently in our data archives, like letters that have been delivered but not yet opened. It takes the right combination of technology, technique, and human insight to recognize what we're looking at. This delayed recognition is more common in astronomy than one might expect. The universe is vast and full of subtle phenomena that can easily escape notice until we develop the right tools or perspectives to recognize them. Ammonite's story reminds us that discovery is often less about finding something completely new and more about learning to see what was always there. The international nature of this discovery reflects the truly global character of modern astronomy. Scientists from Taiwan worked alongside colleagues from Japan, Canada, Korea, and China, sharing data and insights across continents and time zones. The Subaru telescope itself represents this spirit of international cooperation, a Japanese facility that serves astronomers from around the world, perched on Hawaiian soil that has become a window to the cosmos for all humanity. This collaborative approach is essential when studying objects as rare and distant as sednoids. No single institution or country has all the resources needed to conduct such research. The specialized cameras, the computational power needed for orbital calculations, the expertise required to interpret the data, all of these elements must come together in a carefully coordinated effort that spans years and involves dozens of researchers. The naming convention for these distant objects also tells a story about how we relate to the cosmos. The formal designation 2023 KQ-14 follows the systematic approach that astronomers use to catalogue their discoveries, but the nickname Ammonite reflects our very human need to give personality and meaning to the objects we study. By comparing this distant world to an ancient fossil, the research team created a bridge between the familiar and the alien, between the deep past of our planet and the deep past of our solar system. This poetic naming choice also highlights the role that imagination plays in scientific discovery. While the work of detecting and studying Ammonite required rigorous mathematical analysis and careful observational techniques, the human story of this discovery is enriched by metaphor and narrative. Science is not just about numbers and equations. It's about understanding our place in the universe and finding meaning in the patterns we observe. The technological achievement represented by this discovery cannot be overstated. The hypersuprime used to detect Ammonite is a marvel of engineering, containing 116 charge-coupled devices that work together to create images with nearly 900 million pixels. This instrument can detect objects so faint that they emit less light than a candle would produce if viewed from thousands of miles away. But even with such sophisticated technology, finding Ammonite required what astronomers call the blink technique, comparing images taken at different times to look for objects that move against the background stars. It's a method that dates back to the early 20th century discovery of Pluto, updated with modern digital sensors and computer processing, but still fundamentally relying on the patient human eye and mind to spot patterns in the data. The orbital mechanics that govern Ammonite's journey through space represent some of the most elegant physics in the universe. Its elliptical path follows the same mathematical principles that were first described by Johannes Kepler over 400 years ago. Yet the extreme nature of its orbit pushes these classical concepts to their limits. The gravitational forces that keep Ammonite bound to our solar system are so subtle that they barely overcome the tendency for this distant world to drift away into interstellar space. This delicate balance between gravitational attraction and orbital velocity has persisted for billions of years, a testament to the fundamental stability of our solar system. Despite the apparent chaos of planetary formation, despite the gravitational perturbations from passing comets and asteroids, despite the slow evolution of our sun's luminosity over geological time, Ammonite has maintained its ancient dance around our star. The computer simulations that confirm this orbital stability represent another triumph of modern astronomy. Researchers can now model the gravitational interactions of our solar system with extraordinary precision, tracking the positions of planets, moons, and smaller bodies across billions of years of simulated time. These virtual experiments allow us to test hypotheses about the past and future evolution of our cosmic neighborhood in ways that would have been impossible just a few decades ago. When these simulations are run backward in time, they reveal a fascinating story about the early solar system. The fact that Ammonite and its fellow sednoids may have once shared similar orbital orientations suggests that the outer regions of our solar system were once organized quite differently than they are today. Something dramatic must have occurred to scatter these objects into their current diverse paths. The nature of this ancient scattering event remains one of the great mysteries of planetary science. Was it the passage of a nearby star during our sun's youth in a crowded star cluster? The gravitational influence of a planet that was later ejected from our solar system? Or perhaps something even more exotic, like the disruption caused by a close encounter with a brown dwarf or massive planet from another star system? Each of these possibilities paints a different picture of our solar system's violent youth. The early stages of planetary formation were far from the orderly process we might imagine. Instead, they were characterized by chaos, collision, and constant change. Entire worlds may have been hurled into interstellar space, while others were scattered into the distant orbits we observe today. The implications of Ammonite's discovery extend beyond our solar system to our understanding of planetary formation around other stars. If our own cosmic neighborhood harbors such a sparse population of distant objects, what might we expect to find around other stars? The detection of sednoids in alien solar systems would provide crucial insights into the universality of the processes that shaped our own system. Current technology limits our ability to detect such distant objects around other stars, but future space telescopes may change this situation dramatically. The same techniques that led to Ammonite's discovery could potentially be applied to nearby star systems, revealing whether the phenomenon of detached objects in highly elliptical orbits is unique to our solar system or a common feature of planetary system evolution. The story of Ammonite also illustrates the importance of long-term astronomical surveys. This discovery was made possible by the Fossil Project, a systematic effort to map the outer solar system using state-of-the-art technology. Such surveys represent a significant investment of time and resources, but they're essential for advancing our understanding of the cosmos. Future surveys promise to reveal even more secrets of the outer solar system. The Vera Rubin Observatory, currently under construction in Chile, will scan the entire southern sky every few nights, potentially discovering hundreds or thousands of new trans-Neptunian objects. The Nancy Grace Roman Space Telescope will peer even deeper into space, possibly detecting objects so distant and faint that they're currently beyond our reach. These future discoveries will help us determine whether Ammonite is truly unusual or simply the first of many similar objects waiting to be found. The answer to this question will have profound implications for our understanding of solar system formation and the prevalence of planetary systems like our own throughout the galaxy. As we contemplate Ammonite's lonely vigil in the outer darkness, it's worth considering what this discovery means for our sense of cosmic perspective. Here is an object that has existed for billions of years, following the same orbital path with mechanical precision, indifferent to the rise and fall of civilizations on distant Earth. It serves as a reminder that the universe operates on scales of time and space that dwarf human experience. Yet through the application of human ingenuity and scientific method, we have managed to detect and study this distant world. We've calculated its orbit, estimated its size, and placed it within the broader context of solar system evolution. In doing so, we've extended our understanding far beyond the bounds of our home planet, reaching out across the void to touch, however briefly, this ancient wanderer from the solar system's youth. The discovery of Ammonite represents more than just another entry in the catalogue of known solar system objects. It's a testament to our species' endless curiosity about the cosmos and our remarkable ability to make sense of the universe around us. In the gentle glow of telescope light reflecting off this distant world, we see not just a chunk of rock and ice, but a bridge connecting us to the deepest mysteries of cosmic evolution. In the quiet contemplation of Ammonite's discovery, we find ourselves face to face with one of the most profound questions in astronomy. What does it mean to be alone in the vastness of space? This distant world has spent billions of years in solitude, following its ancient path through the cosmic darkness with no companion save the distant pull of our sun's gravity. Yet in that solitude lies a story that connects us to the very origins of everything we know. The technical challenges of studying such a distant object are staggering. When astronomers observe Ammonite, they're not seeing it as it is now, but as it was hours ago when the faint sunlight reflecting off its surface began its journey toward Earth. This tiny delay reminds us that all astronomy is, in essence, a form of time travel. We're always looking backward into the past, piecing together the history of the universe, one photon at a time. The light that reaches us from Ammonite has travelled across billions of miles of empty space, carrying with it the only information we have about this distant world. In that faint glow, encoded in wavelengths and intensities that require the most sensitive instruments to detect, lies everything we can know about Ammonite's composition, size, and surface properties. It's remarkable that we can learn so much from so little. The spectroscopic analysis of this distant light reveals clues about what Ammonite is made of. Like other objects in the outer solar system, it's likely composed primarily of water ice, mixed with rocky material and organic compounds. These are the building blocks of the early solar system, the primordial ingredients from which planets and moons eventually formed. In studying Ammonite's composition, we're essentially examining a sample of the raw materials that existed when our cosmic neighborhood was young. The surface of Ammonite, never warmed by anything more than the distant whisper of sunlight, preserves conditions that haven't changed significantly in billions of years. Unlike the surfaces of inner planets, which are constantly reshaped by weather, tectonics, and other dynamic processes, Ammonite's surface is a frozen archive of the early solar system. Every crater, every ridge, every subtle variation in its landscape tells a story about the bombardment history of our solar system's youth. The discovery of Ammonite also raises fascinating questions about the nature of space and time in the outer solar system. At such vast distances from the Sun, the familiar cycles of day and night, seasons, and weather that define our earthly experience become meaningless. A single orbit around the Sun takes thousands of years, longer than recorded human history. From Ammonite's perspective, Our entire civilization, from ancient Mesopotamia to the present day, would be just a brief moment in its endless journey. This perspective shift is both humbling and oddly comforting. While human concerns often feel overwhelming and urgent, Ammonite's story reminds us that the universe operates on scales that dwarf our immediate worries. There's something peaceful about contemplating this distant world's patient journey through space, following the same path it has travelled for longer than complex life has existed on Earth. The mathematical precision required to calculate Ammonite's orbit represents one of humanity's greatest intellectual achievements. Using nothing more than observations of a faint point of light moving slowly across the sky, astronomers can predict exactly where this object will be thousands of years from now. This ability to peer into the future through mathematical models is perhaps one of the most remarkable aspects of modern science. The equations that govern Ammonite's motion are the same ones that describe the fall of an apple from a tree or the swing of a pendulum. Yet when applied to objects at such vast distances and timescales, these simple mathematical relationships reveal the deep underlying order of the cosmos. There's something almost mystical about the way a few elegant equations can capture the essence of motion across such enormous scales. The gravitational forces that keep Ammonite bound to our solar system are incredibly subtle. At its farthest point from the Sun, our star's gravitational pull is millions of times weaker than what we experience on Earth's surface, yet it's still strong enough to prevent this distant world from drifting away into interstellar space. This delicate balance between attraction and escape has persisted for billions of years, a testament to the fundamental stability of gravitational systems. The study of Ammonite's orbit also provides insights into the nature of chaos and stability in dynamic systems. While its path appears perfectly predictable over millions of years, tiny perturbations from passing comets or distant planetary alignments could potentially accumulate over geological time to produce dramatic changes in its trajectory. This sensitivity to initial conditions is a hallmark of chaotic systems, yet Ammonite's orbit has remained remarkably stable throughout the age of the solar system. The discovery process itself illustrates the importance of patience in scientific research. Unlike the dramatic eureka moments often portrayed in popular culture, the identification of Ammonite required years of careful observation, data analysis, and verification. The initial detection was followed by months of follow-up observations to confirm that this wasn't just a background star or instrumental artifact. Only after this painstaking verification process could astronomers confidently announce the discovery of a new world. The international collaboration that made this discovery possible represents science at its finest. Researchers from different countries, speaking different languages and working in different time zones, came together around their shared fascination with the cosmos. The data flowed freely across borders, analysed by teams that combine their expertise to extract maximum information from every precious photon of light captured by the telescope. This spirit of international cooperation is particularly important in astronomy, where the objects of study belong to no single nation or culture. The cosmos is humanity's shared heritage, and discoveries like Ammonite belong to all of us. In an age of increasing division and conflict, the peaceful collaboration required for such discoveries offers a glimpse of what humanity might achieve when we work together toward common goals. The naming of Ammonite after those ancient spiral fossils reflects the deep human need to find connections between the familiar and the strange. By comparing this distant world to creatures that once swam in prehistoric seas, the research team created a bridge between Earth's biological past and the solar system's cosmic history. Both represent preserved remnants of ancient worlds, windows into times so distant that they challenge our ability to comprehend the vast scales of natural history. The preservation of orbital characteristics over billions of years makes Ammonite a kind of gravitational fossil, maintaining the signature of ancient forces that shaped the outer solar system. Just as paleontologists study fossilized bones to understand extinct creatures, astronomers study the orbits of distant objects to understand the forces that sculpted our cosmic neighborhood during its youth. The implications of Ammonite's discovery extend far beyond our solar system. If such objects exist in the outer reaches of our cosmic neighborhood, they likely exist around other stars as well. The detection of similar objects in alien solar systems would provide crucial insights into the universality of planetary formation processes and the prevalence of systems like our own throughout the galaxy. Current technology limits our ability to detect such distant objects around other stars, but future space telescopes may change this dramatically. The same techniques that led to Ammonite's discovery could potentially be applied to nearby star systems, revealing whether detached objects in highly elliptical orbits are unique to our solar system or a common feature of planetary system evolution. The story of Ammonite also highlights the importance of technological innovation in advancing scientific knowledge. The discovery was made possible by cutting-edge instruments like the Hyper-Suprime Cam, which represents years of engineering development and technical refinement. Each new generation of telescopes and detectors opens new windows on the universe, revealing phenomena that were previously invisible to human observation. The data processing techniques used to identify Ammonite among the countless background stars represent another triumph of modern computational astronomy. Sophisticated algorithms can now sift through vast amounts of observational data, identifying patterns and signals that would be impossible for human observers to detect manually. This marriage of advanced instrumentation and computational power is revolutionizing our ability to explore the cosmos. As we consider the broader implications of Ammonite's discovery, it's worth reflecting on how this finding fits into the grand narrative of cosmic evolution. From the initial collapse of a giant molecular cloud to form our sun and planets, through the chaotic early bombardment period, to the gradual settling into the stable configuration we observe today, our solar system has undergone a remarkable transformation over billions of years. Ammonite serves as a witness to this entire epic story. It formed during the earliest phases of planetary accumulation, survived the violent reshuffling of the outer solar system, and has maintained its ancient orbital characteristics through geological ages. In its patient journey through space, we see reflected the deeper rhythms of cosmic evolution that operate on scales far beyond human experience. The discovery also reminds us of how much we still don't know about our own cosmic neighborhood. Despite centuries of astronomical observation and decades of space exploration, we're still finding new worlds in our solar system. Each discovery like Ammonite forces us to revise our understanding of how planetary systems form and evolve, adding new pieces to the grand puzzle of cosmic history. The rarity of sednoids like Ammonite makes each discovery precious. With only 4 known examples in our entire solar system, these objects represent an extremely sparse population of survivors from the early phases of planetary formation. Their orbits carry information about ancient processes that shape the outer solar system, information that would be lost if these objects hadn't survived to the present day. Future surveys promise to reveal more of these elusive objects, potentially discovering dozens or hundreds of additional sednoids in the coming decades. Each new discovery will add to our understanding of the outer solar system structure and evolution, helping us piece together a more complete picture of how our cosmic neighborhood came to be. The technological challenges of detecting and studying such distant objects continue to push the boundaries of astronomical instrumentation. Future telescopes will need to be even more sensitive and sophisticated to detect the faintest members of this population. The development of these advanced instruments will likely yield unexpected discoveries and open new avenues of research that we can barely imagine today. As we drift toward the conclusion of our gentle exploration of Ammonite's story, it's worth considering what this discovery means for our understanding of time and permanence in the universe. Here is an object that has maintained its essential characteristics for longer than complex life has existed on Earth, following the same orbital path with mechanical precision through countless cosmic seasons. Yet even Ammonite's seemingly eternal journey is not truly permanent. Over timescales measured in trillions of years, the slow evolution of our Sun and the gradual decay of orbital energy will eventually alter its path. The universe itself is evolving, and even the most stable configurations will eventually give way to new arrangements of matter and energy. This tension between stability and change, between permanence and transformation, lies at the heart of our understanding of cosmic evolution. Ammonite represents a moment of stability in the endless dance of gravitational forces, a pause in the cosmic symphony that has lasted for billions of years but will not last forever. In the quiet darkness of space, Ammonite continues its ancient journey, carrying within its orbit the memory of our solar system's youth. It serves as a reminder that the universe is full of wonders waiting to be discovered, stories waiting to be told, and mysteries that challenge our understanding of the cosmos and our place within it. The gentle rhythm of Ammonite's orbit, measured in millennia rather than minutes, offers a different perspective on the passage of time. While we measure our lives in days and years, this distant world marks time in geological epochs, its position in space serving as a cosmic calendar that records the slow turning of the celestial spheres. As we settle into the comfort of this cosmic perspective, we find ourselves connected to something far greater than our immediate concerns. In the patient journey of Ammonite through the outer darkness, we see reflected the deeper rhythms of the universe, the quiet persistence of natural law, and the remarkable ability of scientific inquiry to reveal the hidden connections that bind us to the stars. The discovery of Ammonite opens a window into one of the most intriguing aspects of modern astronomy: the delicate interplay between observation and theory that drives scientific progress forward. Each new piece of data gathered about this distant world forces researchers to refine their models and adjust their understanding of how the outer solar system behaves. It's a continuous dance between prediction and discovery, where each step reveals new complexities that weren't visible from our previous vantage point. The process of confirming Ammonite's existence illustrates the methodical nature of astronomical research. Unlike the dramatic discoveries often portrayed in science fiction where new worlds are revealed in sudden moments of revelation, the reality involves months of careful verification, cross-checking observations against known catalogues of stars and asteroids, and ruling out instrumental artifacts or data processing errors. Every potential discovery must run this gauntlet of scrutiny before it can be accepted as genuine. The archival nature of Ammonite's detection story highlights an often overlooked aspect of modern astronomy: the vast digital libraries of sky images that accumulate over decades of observation. These archives contain countless treasures waiting to be discovered by future generations of researchers who will have better tools and techniques for extracting information from the data. It's as if the universe has been leaving breadcrumbs for us to follow, and we're only now learning to see the trail. The collaborative verification process that confirmed Ammonite's discovery involved multiple independent teams using different telescopes and techniques to measure its position and motion across the sky. This redundancy is essential in astronomy, where a single misidentified star or processing error could lead to false claims of discovery. The convergence of multiple independent measurements provides the confidence needed to announce the existence of a new world. The orbital calculations that define Ammonite's path through space represent some of the most precise mathematical work in all of science. Using observations spanning nearly 2 decades, astronomers have determined its position with an accuracy that would allow them to predict where it will be centuries from now. This mathematical precision emerges from the fundamental predictability of gravitational systems, where the same forces that govern falling apples also control the motion of distant worlds. The computer simulations that model Ammonite's orbital evolution backward through time reveal fascinating glimpses of our solar system's dynamic history. These virtual experiments can explore scenarios that would be impossible to test through direct observation, running the clock of cosmic evolution in reverse, to see how current configurations might have emerged from different initial conditions. It's like having a time machine that operates through mathematics rather than exotic physics. The statistical analysis of sednoid orbits provides insights into the population dynamics of these rare objects. With only 4 known examples, the sample size is frustratingly small, but patterns are beginning to emerge that hint at the underlying processes that shape their distribution. Each new discovery adds crucial data points to this sparse dataset, potentially revealing trends that are invisible when looking at individual objects in isolation. The observational bias that affects sednoid detection represents one of the most challenging aspects of studying these distant objects. Our ability to find them depends strongly on where they happen to be in their orbits. When we look, and certain regions of the sky are much easier to search than others. This creates systematic gaps in our knowledge that must be carefully accounted for when drawing conclusions about the overall population. The photometric properties of Ammonite, the way it reflects and absorbs different wavelengths of light, provide clues about its surface composition and structure. These subtle variations in brightness across the spectrum can reveal the presence of water, ice, organic compounds, and rocky minerals that make up its outer layers. It's remarkable that we can learn so much about the composition of an object so distant that it appears as nothing more than a faint dot of light. The rotation period of Ammonite, if it can be determined from variations in its brightness, would provide insights into its internal structure and formation history. Objects that form through accretion of smaller pieces tend to have different rotation characteristics than those that were broken off from larger bodies through collisions. The spin rate serves as a kind of fossil record of the violent or gentle processes that shaped these distant worlds. The thermal properties of Ammonite's surface, where temperatures hover just above absolute zero, create conditions unlike anything found on Earth. At such extreme, cold water ice becomes as hard as rock, and other materials take on properties that would seem alien to our earthbound experience. Understanding these conditions is crucial for interpreting the physical processes that have shaped Ammonite's surface over billions of years. The gravitational environment around Ammonite is so weak that a person could easily escape its pull with a gentle jump. This highlights the delicate balance that keeps such small objects bound together over geological time. The forces that hold Ammonite's material together are primarily molecular rather than gravitational, making it more like a loosely bound rubble pile than a solid rocky world. The impact history recorded on Ammonite's surface tells a story of bombardment by smaller objects over billions of years. Each crater represents a moment when a comet or asteroid fragment struck this distant world, leaving a permanent scar in its ancient landscape. The size distribution and density of these impacts provide insights into the population of small objects that have wandered through the outer solar system over time. The chemical evolution of Ammonite's surface materials under constant exposure to cosmic radiation and solar wind creates a thin layer of altered compounds that may be quite different from the pristine interior. This space weathering process gradually changes the optical properties of the surface, making it difficult to infer the original composition from current observations. It's like trying to read a book whose pages have been slowly fading for billions of years. The magnetic field environment around Ammonite is essentially non-existent, given its small size and lack of internal heat sources. This absence of magnetic protection means that charged particles from the solar wind can directly interact with its surface, creating a slow but steady erosion process that has been operating throughout its history. The accumulated effects of this erosion may have significantly altered the object's original appearance. The seasonal variations in Ammonite's distance from the Sun create subtle changes in its surface temperature and the sublimation rate of any volatile compounds. During its closest approach to the Sun, still incredibly distant by earthly standards, there may be a barely detectable increase in activity as frozen gases slowly transition to vapor. These seasonal cycles operate on timescales of thousands of years, rather than the familiar annual rhythm we experience on Earth. The gravitational perturbations that Ammonite experiences from distant planets are incredibly subtle, but measurable with modern precision. These tiny influences accumulate over time, creating long-term changes in its orbital characteristics that can be detected through careful observation. The ability to measure such minute effects represents a triumph of observational astronomy and computational modeling. The resonance relationships between Ammonite's orbit and those of the outer planets reveal the complex gravitational choreography that governs motion in the outer solar system. These mathematical relationships, where orbital periods are related by simple ratios, can either stabilize or destabilize an object's path through space. Understanding these resonances is crucial for predicting the long-term evolution of Ammonite's orbit. The tidal forces experienced by Ammonite from the Sun and planets are vanishingly small, but still play a role in its long-term evolution. These forces tend to circularize orbits over extremely long timescales, potentially explaining why some ancient objects have more circular paths than others. The time required for significant tidal evolution far exceeds the current age of the solar system, making these effects visible only in computer simulations. The escape velocity from Ammonite's surface is so low that particles knocked loose by micrometeorite impacts can easily achieve orbital velocity around the object. This creates the possibility of temporary dust clouds or debris rings that might form and dissipate over short periods. Such ephemeral phenomena would be incredibly difficult to detect from Earth, but could provide insights into the ongoing erosion processes affecting the surface. The albedo or reflectivity of Ammonite's surface provides clues about its composition and history. Objects with high albedo tend to be covered in fresh ice or light-colored minerals, while those with low albedo may be coated in organic compounds or space-weathered materials. The measured albedo of Ammonite fits within the range expected for objects in the outer solar system, but each measurement adds to our understanding of surface processes in these extreme environments. The phase curve behavior of Ammonite, the way its brightness changes as the angle between Earth, Sun, and object varies, can reveal information about surface texture and composition. Rough surfaces tend to scatter light differently than smooth ones, and certain minerals have characteristic phase curve signatures. These subtle photometric effects require extremely precise measurements, but can provide detailed insights into physical properties. The color variations across Ammonite's surface, if any exist, would indicate compositional differences or varying degrees of space weathering. Such variations might result from impacts that have exposed fresh material or from the preferential erosion of certain compounds over others. Current observations lack the resolution to detect surface features, but future missions might reveal a complex and varied landscape. The outgassing potential of Ammonite during its closest approach to the Sun represents an intriguing possibility for future observation. While the heating is minimal compared to inner solar system conditions, it might be sufficient to sublimate small amounts of volatile compounds, creating a tenuous atmosphere or even a faint tail. Such activity would be extremely difficult to detect, but would provide direct evidence of the object's composition. The formation scenario for Ammonite likely involved the gradual accumulation of smaller, icy and rocky particles in the outer regions of the early solar system. This process would have been slow and gentle, allowing materials to stick together through weak gravitational and molecular forces. The resulting object would be a heterogeneous mixture of the various compounds that were available in that region of space during the formation epoch. The internal structure of Ammonite is probably quite different from that of inner solar system objects. Rather than having distinct layers of different materials, it likely consists of a relatively homogeneous mixture of ice and rock with significant porosity. This structure would make it quite fragile and susceptible to disruption by impacts or tidal forces, but also explains how such objects can survive for billions of years in the gentle environment of the outer solar system. The dynamical history of Ammonite reveals the complex interplay between gravitational forces that has shaped the outer solar system over billions of years. Its current orbit represents a delicate balance between various perturbations that have nudged it back and forth over time. Understanding this history requires sophisticated computer models that can track the positions and velocities of multiple objects across vast timescales. The discovery techniques that led to Ammonite's identification represent the cutting edge of astronomical technology and data processing. The ability to detect such faint objects requires not only sensitive instruments, but also sophisticated algorithms that can distinguish genuine celestial objects from instrumental noise and background contamination. These techniques continue to improve, opening new windows on the distant universe. The follow-up observations that confirmed Ammonite's existence demonstrate the importance of patience and persistence in astronomical research. Initial detections must be verified through multiple independent measurements using different instruments and techniques. This process can take months or years, but is essential for building the confidence needed to announce significant discoveries. The orbital integration studies that predict Ammonite's future path through space reveal the remarkable stability of its motion over geological timescales. Despite the complex gravitational environment of the outer solar system, this distant world will continue following essentially the same path for millions of years to come. This stability is what makes it such a valuable probe of ancient conditions in the outer solar system. The comparative analysis of Ammonite with other sednoids reveals both similarities and differences that provide insights into the formation and evolution of this rare population. While all sednoids share certain orbital characteristics, each has its own unique properties that reflect the specific conditions and processes that shaped its individual history. These comparisons help astronomers understand the range of possible outcomes for objects in the outer solar system. The observational challenges posed by Ammonite's extreme distance and faintness push the limits of current astronomical capabilities. Even with the largest telescopes and most sensitive detectors, this object appears as barely more than a few pixels of light against the star-filled background. Extracting meaningful information from such sparse data requires sophisticated analysis techniques and careful statistical methods. The implications of Ammonite's discovery extend beyond our solar system to our understanding of planetary formation around other stars. If such objects are common in the outer reaches of planetary systems, they might be detectable around nearby stars using future space-based telescopes. Such discoveries would provide crucial insights into the universality of the processes that shaped our own cosmic neighborhood. The archival mining efforts that revealed Ammonite's presence in older observations demonstrate the lasting value of astronomical data. Images and measurements that seemed routine when first obtained can later prove to contain hidden treasures when analysed with new techniques or viewed in the context of subsequent discoveries. This highlights the importance of maintaining comprehensive data archives for future generations of researchers. The international collaboration that made Ammonite's discovery possible reflects the global nature of modern astronomy. Scientists from different countries and institutions work together, sharing data, expertise, and resources to achieve a common goal. This spirit of cooperation is essential for tackling the complex challenges of understanding our place in the universe. The theoretical implications of Ammonite's orbital characteristics continue to ripple through the astronomical community as researchers work to understand what this discovery means for our models of solar system formation and evolution. Each new piece of information about this distant world forces scientists to refine their theories and consider new possibilities for how the outer solar system came to be. The future prospects for studying Ammonite and similar objects look increasingly promising as new telescopes and instruments come online. The next generation of ground-based observatories will be capable of detecting even fainter and more distant objects, while space-based missions may eventually visit these distant worlds directly. Each technological advance opens new possibilities for understanding these ancient remnants of our solar system's youth. The patient work of tracking Ammonite's motion across the sky continues as astronomers gather more data points to refine their understanding of its orbit and physical properties. Each new observation adds to the growing database of information about this distant world, helping to paint an ever more detailed picture of its characteristics and history. As we contemplate the significance of Ammonite's discovery, we find ourselves reminded of the vastness and complexity of the universe around us. This single distant object represents just one piece of a much larger puzzle that astronomers are working to solve. Yet, in its lonely journey through the outer darkness, we can glimpse something of the grandeur and mystery that continues to drive human curiosity about our cosmic home. The story of Ammonite serves as a gentle reminder that the universe is full of wonders waiting to be discovered. In the quiet darkness of space, this ancient world continues its billion-year journey, carrying with it the memories of our solar system's youth and the promise of future discoveries yet to come. Through patient observation and careful analysis, we slowly piece together the epic story of how our cosmic neighborhood came to be, and perhaps catch a glimpse of what lies ahead in the vast expanse of space and time. Vast expanse of space and time.